Okay, so from last class we learned about the definitions of sine, cosine, and tangent. We talked about the vertical and horizontal displacement, but we can give them cute little letter names where sine is y over r, cosine is the x coordinate or horizontal displacement over r, and since tangent is the vertical displacement over the horizontal displacement, it is sine over cosine or y over x. So this is a shortcut version. Instead of writing out the words horizontal and vertical displacement, we have these cute little letters. But what if we wanted to use the definitions to determine the value of the trig ratios for a certain angle theta? If we wanted to use the angle theta to determine these coordinate points, instead of having to do what we did last class, let's see if there's a shortcut we could take to determine the coordinate point x and y. So I'm going to zoom in for a second on this unit circle or this circle here, and we're going to label some stuff. Pretty obviously, this terminal ray, where it intersects the circle, is the radius of the circle. That's a property of circles that we learned about in geometry class. The radius is the same all the way around the circle. That's how we came up with the set of points that make the circle anyways. If we were to drop down a line, it's called an altitude if this was a triangle. Look at the geometry words. This is an altitude, which means it meets at a right angle. This value right here would be the y distance or the vertical displacement of the point. This is a review from last class. This value here, as we go horizontally or on the x-axis, is the horizontal displacement. This creates that coordinate point that we were using last class, x comma y. But is there a way we can write that coordinate point in terms of the trig function itself to allow us to calculate these coordinate points around the circle easier? The answer is yes. So let's take for a second cosine. Sorry, did you need a second? I pause. If we take the ratio we have for cosine, and the ratio we have for cosine, it's on your paper, cosine of theta is equal to x divided by r. And we want to solve it for the coordinate point that would go into x comma y, which means I want to solve this for x. If I want to get x by itself, what do I have to do to both sides? Multiply by r. So if I multiply by r on both sides, this is going to end up being r cosine of theta equal to x. Well, right there, I have a value. I have a coordinate point, the x value of my coordinate point in terms of r and theta. It is going to be the radius times the cosine of our angle theta. Let's do the same thing for sine. Since the sine function utilizes the coordinate point y, if we take sine of theta equal to y over r, and we solve for y, or the vertical displacement, the y coordinate, just the same way we would multiply both sides by r so that we end up with r sine of theta equal to y. So these different values here, r cosine of theta and r sine of theta, create my coordinate point. Instead of writing the coordinate point P as x comma y, I can write the coordinate point P as r cosine of theta, comma r sine of theta. So this is my x coordinate, and this is my y coordinate. X coordinate, y coordinate. R cosine theta, comma r sine of theta. So that's the radius times cosine to make the x coordinate, and the radius times the sine of theta to make the y coordinate. Now this is going to allow us to find the x and y coordinate for things that are not on pretty coordinate points like 2, 1. We can get decimal values for our coordinate point x and y now that we have these formulas. So for example, suppose we take an angle with a measure of 2 radians and inscribe it in a circle with a radius of 6 units. What are the coordinates where the terminal ray intersects this circle? Okay, so let's look at what we're given. We were told that the angle, the theta, is 2. I'm going to highlight that purple. Here's a new color for us. Theta is 2. I was also told that the radius length is 6, which means this also is 6. Any location of a radius around the circle is going to be the same value of 6. So we have equations to create this coordinate point. we said that that x value, the x coordinate, should be equal to r cosine of theta. Well, guys, what does this problem tell you is the radius? 6. What does this problem tell you is the angle measurement? 2. Very good, because again, 2 radians, I know you're used to looking for degrees when it comes to angle measurements. We're not measuring in degrees in this class. It's going to be all in radians. So we're going to plug in a 2. At that point, there are no variables left. This is a calculator question. So grab your calculator. Number 1, make sure it is in radian mode. Easiest way to do that is to reset your calculator. These calculators reset into radian mode automatically. Now, my geometry classes and my dual credit classes are working in degrees, so they have been changing these calculators to degrees, so make sure you change it back to radians or else you will get the wrong answer. When you type in 6, there's a button for cosine and then 2. Yeah, resetting a second plus 712. Yes, yes, yes. So if we do 6 cosine of 2 in our calculators, you can close that parentheses if you'd like, it gives you approximately negative 2.497 as the value for x. Is that what you guys got? Fabulous. Let's do the same thing for y. Again, we're making sure we worked in radian mode. If you typed 6 cosine of 2 and you didn't get this, you're in degree mode, so please change it to radians. If we do the same thing for the y value, remember the y value is going to be found with r sine of theta. We already know that r is 6 and that theta is 2. So I can just type in my calculator 6 sine of 2. And if I do 6 sine of 2 in radian mode, this would be 5.456, which means I know that the coordinate point P for this circle is negative 2.497, comma, 5.456. Questions, comments, concerns? Okay, as a quick review / leveling it up to working in radians, let's talk about some geometry concepts that we probably haven't thought about since we took geometry 2 or 3 years ago. All right, equilateral triangles. What do we know about equilateral triangles? They're all acute angles. Specifically, all the angles are 60 degrees. I heard somebody else say that all the sides are what? Equal. Congruent would be the geometry term for that. Congruent means that they're all the same. We put the little tick marks on them. All the angles do measure 60 degrees, but we're not working in degrees in this class. So we need to change these to radians. If we know an entire semicircle, 180 degrees is pi, what is 60 degrees? What do you have to do to 180 to get 60? Divide by 3. So what am I going to do to pi? Divide by 3. All of the angle measurements in an equilateral triangle are pi over 3 radians. So when you draw a 60-degree angle, instead of writing 60 degrees, you're going to write pi over 3 for me for the rest of this class. We're not working in degrees, we're working in radians. If you need to translate degrees to radians every time you work a problem, that's fine too. Sometimes my brain works that way since we got so used to degrees for all of our life, but we do need to be working in radians. All right, another geometry concept is a right triangle. In a right triangle, what does one of the angle measurements measure? 90 degrees, but I want it in radians. If 90 degrees is half of a semicircle, pi over 2, very good. So instead of writing 90 degrees for me for the rest of this class, you're going to write pi over 2. We also need to review Pythagorean theorem. Everybody's favorite theorem from middle school. To do this, I'm going to label the sides A, B, and C. I'm specifically choosing C as my hypotenuse because we need to make sure C is the longest side. Then we have our B value and we have our A value. What is Pythagorean theorem, y'all? Very good. We love that one. A squared plus B squared equal to C squared. The square of the side lengths is equal to the square of the hypotenuse when you add them together. Don't forget about Pythagorean theorem. He will come in handy a lot. Last but not least, we have an isosceles right triangle. Important to remember. What does the isosceles right triangle part tell me if it's isosceles? Two sides are congruent. So if we notice in this image, these two sides are congruent. So we're going to put the little congruent marks. That also means that two of my angles are congruent. Two sides are congruent, forces two angles to be congruent. Now, one of these angle measurements, since it is a right triangle, obviously you can see here is 90 degrees or pi over 2. Now, what about those other two angles? Pi over 4, very good, because there needs to be two of them to equal pi over 2. So pi over 2 divided by 2. Oh, I just wrote pi over 2. Ignore, this should be a 4. So 45 degrees is pi over 4 radians. Fabulous. We feel good about this reminder of some things from geometry. The only new thing is I'm going to measure things in radians instead of degrees. So if you need to flip back and forth for these radian measures, they're on the front of your notes. Let's go on the inside. Let's use these geometry concepts to define some special coordinates for ourselves around a circle. These special triangles create some of the most commonly referred to triangles in trigonometry. Our 45, 45, 90 and our 30, 60, 90 triangles from geometry class are going to create some really important coordinate points for us around the unit circle. So we are going to determine the coordinate point of P if theta is equal to pi over 4. Now for pi over 4, just because we're used to thinking in degrees, what degree measurement am I talking about when I say pi over 4? 45 degrees. Okay, cool. Just because I think it would be helpful to have that on your notes, we're going to leave that there. Now, 45 degrees is like a fourth of a semicircle. So if I were to draw 45 degrees or pi over 4, it would look something like this, where this measurement right here is pi over 4. Let's drop down a straight line to represent the vertical displacement and highlight the horizontal displacement for that coordinate point. If we do this right and we drop down an actual vertical line, this creates a right angle here. What kind of triangle did I just make? A right triangle. More specifically though, what kind? An isosceles right triangle. We know this because it's 45 degrees. It's pi over 4. So these two sides are going to be congruent. I need to know the length of these sides. The problem, if you read up at the top, it tells me that the radius for all these problems is going to be 1. So if I know if this measurement is 1, we need to know the side lengths for x and y. Since this is a right triangle, we can use Pythagorean theorem to do this. If we have a squared plus b squared equal to c squared, and fill in what we know, we don't know a and b, but we do know they're congruent. So what if I change their letters from a and b and just make them s for side length? This becomes s squared plus s squared equal to 1 squared. Where'd the 1 come from? It says the radius is 1, c is the radius. It's the hypotenuse. Well, I've got c squared plus c squared. What can I do with that? C squared, s squared. What is s squared plus s squared? 2s squareds. 1 squared is 1. Can we solve for that letter s? What do I do on both sides? Divide by 2. Then what? Square root. When we take the square root, we need to make sure we put the plus or minus in front of it. So we're taking the square root of 1/2, plus or minus. Now we're going to have to actually split this square root to both the top and bottom. That is a property of radicals that we can do this. What is the square root of 1? Oh yeah, 1. Oof, our brains are asleep. Okay, what's the square root of 2? Is it a cute number, I guess I should say? No, it turns into an irrational number, so we're going to leave it as square root of 2. Now the problem is, convention has us to where we're not allowed to leave radicals in the denominator. I don't know if you did this last year in Algebra 2, but do the words rationalizing your denominator mean anything to you? This is an honest question. I don't know how much I need to explain here. No, I'm seeing blank faces. Okay, you're not allowed to leave rationals or radicals in the denominator. So to get rid of them, you're going to multiply. I'll do this in a different color so you can see. I'll do it in pink. You're going to multiply the top and bottom by whatever is in the denominator that we want to go away. That means I'm multiplying by 1. I'm not changing this number at all because root 2 over root 2 cancels out. It's 1. When I do 1 times root 2, I get root 2 on the top. And when I do square root of 2 times square root of 2, what happens? Basically, those square roots are going to cancel out because it's like I'm squaring it. So this becomes 2. That's called rationalizing the denominator. From here on out, you're not allowed to leave a radical in the denominator. You must fix it. I will count it wrong. Now, to finish this problem out, we still need to know the value of s. S is a distance. So does it make sense to have a negative distance? No, so we're going to drop the negative part of our plus or minus, and we're just going to say that that side length is square root of 2 over 2. Now, again, you might be thinking to yourself, why did we do all of this? It's a great question. Remember, we set out to figure out this coordinate point here. The coordinate point requires us to have an x value and a y value. How far did I travel if I've traveled this x distance? S. What did we just find out was s? Square root 2 over 2. How much did I travel this vertical distance? S. And what did we just find out was s? So we can say for a 45-degree angle, a pretty commonly used angle, the coordinate point P will be square root of 2 over 2, comma square root 2 over 2. That's my x and my y. That's what we wanted. We wanted the coordinate point P for 45 degrees. We just had to do a bunch of geometric algebra to figure out the side distance, the x coordinate and the y coordinate. Before we move on, I know you have questions, so look back through the problem and see where your questions are. Okay, thank you for asking questions. Let's go to the next one because maybe if we see another time of doing this with a different angle measurement, it might understand what we're doing. So this time, I want us to find the coordinate point of P if theta is equal to pi over 3. Now again, pi over 3 is what angle measurement if I were to change this to degrees? 60 degrees. If you have to translate it back and forth in your head, that's fine, but answers and questions will always be in radians for this class. Now, if I were to draw a 60-degree angle here, or a pi over 3 radian angle, it would look something like this, because the entire top 2 quadrants, the entire semicircle at the top, will be split into 3 pi pieces, so this is approximately correct. And I know that this angle right here is pi over 3. I know my radius is 1, so if we draw my triangle here, by dropping down a vertical displacement and highlighting our horizontal displacement, we know that we have y here and we have x here. I also know that because this is a right angle, that I have pi over 2 radians as that measurement. What's the missing measurement up there? Do y'all know? Here's how we figure this out. We know that all 3 angles in a triangle have to add up to 180 degrees, which means all 3 angles in a triangle have to add up to pi. So if we take away what we know, the way you solved in geometry class, we'd be subtracting pi over 3 and then subtracting pi over 2. The problem is it's subtracting fractions, and we always panic when we subtract fractions, but we're not going to panic. If we get a common denominator here, the common denominator would be 6. So I just change all of the fractions to have the common denominator of 6. Are we following? Yeah, okay. All of those fractions are the same thing, yeah? 6 over 6 is 1. 2 over 6 is a third. 3 over 6 is a half. So what's left? What is 6 minus 2 minus 3? 1. So this is just going to be pi over 6. So we have our triangle here. It is no longer a 45, 45, 90 triangle. This is a 30, 60, 90 triangle. Or, in radians, a pi over 3, pi over 6, pi over 2 triangle. Okay, let's copy what we did before. Let's use Pythagorean theorem and figure out what we have and what we need to solve for. We have a squared plus b squared equal to c squared. Pretty obviously, we know that c is going to be 1. It's given to us in the problem that the radius of the circle is 1. We should know one other measurement. It's not y. We should be able to know x. The reason we should be able to know x, and don't draw this because you're going to confuse yourself for a second. If we were to finish this triangle out, if this is a pi over 3 triangle or angle, this one would be pi over 3 and this one would be pi over 3. That's an equilateral triangle. This is only halfway between one side and the other. So instead of being a whole radian of 1, what should x be equal to? 0.5. 0.5. So we have a, my horizontal displacement is 0.5, but I'm going to use a half because we like fractions here. And I can figure out what that b value is or what that y value is. Just like we solved for s earlier, let's solve for y. Again, this has to do with the fact that if you double that triangle we made, the 30, 60, 90, it's an equilateral triangle that goes the whole distance, but it stops halfway, so the horizontal displacement is a half. What is 1/2 squared? 1/4. So we have 1/4 plus y squared equal to 1. Subtract 1/4 from both sides. This would be y squared equal to 3/4 because 1 minus a fourth is 3/4. We square root both sides. You guys told me that earlier. So we get plus or minus square root of 3 over 4. We're going to go ahead and split that to the top and bottom. This is what we're allowed to do with radicals. Square root 3 over square root 4. Can one of those reduce? Yeah, what is the square root of 4? 2. So really, this is going to be like the square root of 3 over 2. I dropped the negative because we're measuring a distance. Distance cannot be negative. Okay. We have our coordinate point. And you're like, what? We only solved for one variable. We solved for y. True. But don't we already have a distance for x, a displacement? So we can say that the coordinate point that meets the unit circle when we're measuring pi over 3 radians is 1/2, comma, root 3 over 2. That's our x and our y, our horizontal displacement and our vertical displacement. Last but not least, we're going to do the same thing for pi over 6. Pi over 6, what is that in degrees? 30. We're going to take 180 divided by 6, that's 30 degrees. Again, we're working in radians, but you can think in degrees if you need to while we're learning. So if I were to draw a 30-degree angle or a pi over 6 angle, it would be the top two quadrants split into 6. So it's approximately here. That would make this pi over 6. If I drop down my vertical displacement, I create a right angle, that's pi over 2. And I have my horizontal displacement. Do these numbers look familiar to you? Pi over 6, pi over 2. If you sneak a look back up at the top, which is why I told you not to draw what I drew over yours, what's that third angle measurement? Pi over 3. This is also a 30, 60, 90 triangle, or a pi over 3, pi over 6, pi over 2 triangle. In which case, we already did all the algebra for it. If you take the triangle you got up here, and you just shift it, what is now the vertical displacement? So again, I can't show you on the board because the iPad doesn't shift, but a second ago, it looked like this. and now it looks like this. So if you look at the values, the ratios you had in the other one, we said that that horizontal displacement, which is now my vertical displacement, was a half. So we're going to get that this is now a half. And we said that the horizontal displacement, which was my vertical displacement, was square root 3 over 2. So my coordinate point P for pi over 6 radians is square root 3 over 2, comma 1/2. So before you flip the page, these measurements that we just wrote down for these coordinate points are extremely vital to remember, because there is going to be parts of your tests for me and tests in your AP that are calculator free, and they want exact answers, which means these values of these special right triangle angle measurements are going to be something we need to have memorized. I will teach you tricks to memorize them by the end of class, I promise you. But a great question that you may be asking is, what if these angles go beyond quadrant 1? Because if you notice on the page we just did, all of those angle measurements were in quadrant 1. That's the easy quadrant. That's honestly the one that holds all the answers. But we will have angle measurements that go beyond quadrant 1, so we need to talk about what happens for those. There is an acronym that we can use to remember which coordinate points are positive or negative in regards to sine or cosine. So if we think about just a quadrant, like a coordinate grid, in the first quadrant, my x and y coordinates are all positive, which means the x values are positive and the y values are positive. In the second quadrant, I would have to go a negative horizontal distance and then a positive vertical distance. What about the third quadrant? What should I put down there? Negative, negative. I had to go left and down. Those are both negative directions. What about the fourth quadrant? Positive, negative. I went a positive direction to the right, but then I went down, which is a negative direction. Since these coordinate points now correspond to sine and cosine, that means that I can tell you which of those trig functions will be positive and which ones will be negative, depending on the quadrant we're in. The acronym we're going to use for this is All-Star Trig Class. You write them in order of the quadrants. All, star, trig, class. Oh, snap. Here's what this tells us. It tells us that all of the trig functions are positive in quadrant 1. The S stands for sine. The sine function and its reciprocal are positive in quadrant 2 because of this little plus sign right there. What do you think is positive in the third quadrant? What do you think the T stands for? Tangent. Because both sine and cosine are negative, negative divided by negative would be positive, so tangent is positive. And in the fourth quadrant, which trig function is positive? Cosine. Again, because that first coordinate is positive and cosine is the first coordinate. All-Star Trig Class tells you whether the trig function is going to be positive or negative. That's going to be helpful to hold on to as we work in building our ideas of the unit circle. Before we really go to a unit circle, though, we need to understand that there are multiples of each angle around the unit circle and what those values are. We're actually not going to start with letter A. We're going to start with letter B because it's easiest to draw. In letter B, we are doing a 45-degree angle around the entire circle, a pi over 4 angle. If I do this, that means that the top semicircle, so above this pink line I'm drawing, should be split into 4 pizza pie slices. Well, here it's split into 2, and if I split those 2 in half, have I made 4 pizza slices in the top? Okay, these are going to measure the multiples of pi over 4. This is 0 radians. I've moved nowhere. We go up pi over 4. We go up again, that's 2 pi over 4. Yes, I know that reduces, stick with me. We go another one, this is 3 pi over 4. We go another one. How many pi's over 4 have I used? 4 pi over 4. See how I'm adding pizza slices and I'm adding to my numerator? Yes, I know some of those numbers will reduce, but we're not going to do that here on purpose. We can continue doing this around the bottom. So I take the bottom and I split it into 4 pieces. That would mean this is 5 pi over 4s, 6 pi's over 4, 7 pi's over 4, and all the way back is 8 pi over 4. Yes, I know they reduce. Stick with me. There are 4 of these measures that do not reduce. These are the 4 we need to be able to recognize. Pi over 4 does not reduce. 3 pi over 4 does not reduce. 5 pi over 4 does not reduce. And 7 pi over 4 does not reduce. These are the multiples of pi over 4 that you need to pay the closest attention to. The other multiples are on my axes, which will reduce to some of the easier measurements later. Not quite worried about that just yet. Let's scoot down. We're going to do C. Does yours say pi over 6 or did I fix it to say pi over 3? Okay, great. I just didn't fix mine. Thank you. Okay, for pi over 3, that means the top quadrant above this green line is going to need to be split into 3. Do your best. If I split it into 3, that's about 3. Especially if I get rid of this line right here. You see how that's pretty much split into 3 pizza pie slices. These are the multiples of pi over 3, which means this first one is pi over 3. And then we have 2 pi, oh, not right there, 2 pi over 3 and 3 pi over 3. We can continue going around the circle if we split the bottom into 3 pizza pie slices. Again, visually getting rid of this guy in case that helps you. This would be 4 pi over 3, 5 pi over 3, and 6 pi over 3. These are the multiples of pi over 3 as we go around the circle. If we were counting in degrees, that would be 60, 120, 180, 240, 300, and 360. But we're measuring in radians, which we're not used to, which is why I'm showing you the multiples. There are only 4 multiples of this number I need you to recognize. The ones that do not reduce, which is pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. 3 over 3 reduces to just pi. 6 pi over 3 reduces to just 2 pi. Obviously, we're going to go back. We're going to do the same thing for pi over 6. Now, pi over 6 is 30 degrees, which means we're going to need to make a lot of lines on this guy to make it all the way around. The top quadrant should be split into 6. So if I take just the top, not quadrant, the top semicircle and split it into 6, I would do it something like this. Again, it's not going to be perfect because we're human drawing on a graph. Ooh, that's really bad. Let me try that again. These multiples will be pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, and 6 pi over 6. Do we see how I'm doing this each time? Just adding 1 as we multiply the multiple around the circle. Do the same thing for the bottom to show all of the multiples of pi over 6. Again, doing our best to draw them as accurately as possible. This would be 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and finally, 12 pi over 6. There again are only 4 that do not reduce. So there are 4 I need you to recognize. The 4 that do not reduce are pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. The rest of them will reduce either to one of the pi over 3 multiples or one of my quadrant multiples. The reason I'm having you recognize these different multiples of these numbers is because the trig value is the same for every single one of these multiples with the coordinate points that you just found on the opposite page. The only thing that's going to change is the sign, depending on what quadrant you're in for positive and negative coordinate points, which you can remember with All-Star Trig class. It's not going to make sense till we see some examples and understand the full grasp of the unit circle, which would take us a couple class periods. Okay, this last page right here, it says it's a hand trick for quadrant 1 trig, which it totally is. And since it's quadrant 1, it also helps us with all the rest of the quadrants. But it means that you don't actually have to memorize the coordinate points that I taught you on that second page. However, right now I actually want you to flip to, I'm going to show this page. I want you to flip to this one where we got all of those coordinate points. I want you to be looking at this page while I go over this one. This hand trick for quadrant 1 trig is basically a way for you to always have a way to find the different values using just your left hand. So everybody hold up their left hand, not your right, your left, because it looks like the one on the page. Okay. Do you see that your fingers are going to represent the different angle measurements from smallest to largest? Pinky is 0, thumb is 90 degrees or pi over 2. That means your, what's this one, ring finger is measuring 30 degrees because that's the next biggest, which for us is pi over 6. What is your middle finger representing? 45 degrees or pi over 4. And then your index finger is representing? 60 degrees or pi over 3. Now we can tell all of the trig measures we just found using our hand. So you are looking at the coordinate point we found for 45 degrees for pi over 4. We said that it was square root 2 comma square root 2. Are you looking at your paper and see that? The reason we know that is because if we put down the finger for pi over 4, the sine value is the number of fingers left below the finger you put down. How many fingers are below this? 2 divided by 2. So square root 2 over 2. The cosine value is the number of fingers above the finger you just put down. How many fingers are above my middle finger? 2. Square root 2 over 2. Let's change our angle. Let's find more values. We did pi over 3 next, I believe, yeah? Okay, so we put down our index finger. The sine value, which is your y coordinate on your paper, is the number of fingers below. How many fingers below? 3 over 2. So we said square root 3 over 2 is our y value. How many fingers above? What's the square root of 1? Where's where the 1/2 comes from? Okay, let's do this 30 degrees, which is pi over 6. Put down your ring finger. Sine, which is your y coordinate, is the number of fingers below. How many fingers below? 1, which is where the 1/2 comes from. How many fingers above? 3. So it's square root 3 over 2 for your cosine value, or the x coordinate. Now this also works for tangent, which we didn't really touch the values of tangent because it's the ratio of sine and cosine. And since it's a ratio of sine and cosine, you just do the number of fingers below divided by the number of fingers above. So as a bonus, if I were to ask you what is the tangent of 45 degrees, which finger do I put down for 45 degrees? Middle finger. How many fingers are below? 2. How many fingers are above? What is square root of 2 over square root of 2? 1. The tangent of 45 degrees is 1, period. Okay. What if I asked you to do the tangent of 60 degrees, pi over 3? Which finger do I put down? The index. For tangent, how many fingers are below? 3. How many fingers are above? So it would be square root of 3 over square root of 1. Square root of 1 is 1, so it's just square root of 3. That's the tangent of 60 degrees. Last but not least, we have this one. For 30 degrees, it would be square root of 1 over square root of 3. You would have to rationalize your denominator there, so we're not going to do that one in our head. You'd probably grab a piece of paper for it. If that hand trick is not really working for you because you're not a manual learner, here's the other thing we can do to memorize this. We're going to make yourself a table. You can draw this one anywhere on your notes, by the way. And we're going to have this table have the values for sine of theta, cosine of theta, and tangent of theta. We'll do these in order from smallest to largest, which means we're going to do pi over 6 first, and then pi over 4, and then pi over 3. We've already been over some of these, so let's just talk it through. The sine of pi over 6, I'd put down my ring finger. that would be square root of 1 over 2. The cosine of pi over 6, same finger, is square root 3 over 2. And the tangent, which is below divided by above, is going to be 1 over square root 3. I didn't write this in the thing on purpose. I can't leave an answer with an unrationalized denominator, so I'm multiplying both the top and bottom by root 3 so that this becomes square root of 3 over 3. We switch to pi over 4, which is 45 degrees. It is sine is below. How many fingers are below for 45 degrees? Square root 2 over 2. How many fingers are above? 2. Square root 2 over 2. And if we do below divided by above, you guys already told me that was square root 2 over 2, square root 2, which is 1. Last but not least, for pi over 3, which is 60 degrees, the number of fingers below is pi over 3 over, square root 3 divided by 2. Number of fingers above is square root 1 over 2. And below divided by above would be square root of 3 divided by 1. I don't have to rationalize that because the radical is in the numerator. And yes, we don't have to show the divide by 1 because it's just square root 3. The reason I went through this whole table with you is because from here on out, on practically every formula quiz you take, I will put a blank table and you're going to fill it in. You don't have to memorize the table. You need to memorize how to find the table because it'll allow you to fill it out. There are some patterns, so if you're a pattern person, I'm giving you tons of ways to memorize this. That's why. What do you notice about the pattern for sine? Up here. 1, 2, 3, divide by 2. What do you notice about the pattern for cosine? Divide by 2. Ah! Yeah, you have to remember tangent. That's probably where the hand trick comes in. But look at that. 6 out of the 9 you can do. I will put them in order. Literally, it'll look like this table every time. Because this is something if you can use as a reference tool, meaning you write it down when you start your quizzes or your tests. You write it down when you start your AP test. It is a reference for you. It's something great to build and use every time.